Happy New Year and welcome to the wolfSSL live webinar, new and updated Getting Started with the wolfBoot, presented by wolfSSL Senior Software Engineer Daniele Lacamera. My name is Shizuka and I'll be moderating this webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Also, feel free to email us at fax@wolfSSL.com if you have any additional questions. And now I would like to give a brief company overview before move to the technical presentation. Today, wolfSSL secures over 2.5 billion connections. We have more than 2,500 OEM customers, and that's no resellers. wolfSSL consists of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO-178 support, FIPS certification and a FIPS ready offering, MQTT up to the V5 specification, SSHv2, TPM 2.0, a secure bootloader known as wolfBoot, Java wrappers and JSSE support, commercial support for Coral, and our latest product offering, wolfHSM. These offerings are accompanied by slow maintenance and support plan up to the 24/7 level. We also offer full service consulting. And now I would like to turn it over to Daniela to discuss new and updated Getting Started with wolfBoot.
Thank you very much, Shizuka, and thanks everyone for joining this webinar today, and welcome to this session about getting started with wolfBoot. As Shizuka already said, our product offering focus on three main pillars. So securing data addressed through cryptography, securing data in transit with SSL TLS mainly, but also with other products like wolfSSH, and also securing the boot process. That's where we focus today, and securing firmware updates thanks to wolfBoot and other components like that will help us transferring the firmware for the secure updates. This is a slide that describes a little bit of our product line. As you will see, today we're going to focus on wolfBoot, which is our secure bootloader. That's our universal secure bootloader. Is the main brick, let's say, to build the solutions for remote secure update, secure firmware updates, and secure boot. So wolfBoot is the open source universal secure bootloader. As all our products is distributed with two licenses, a GPL license for the code that is available, as we will see from GitHub or our download page, and a commercial license in case you want to integrate in proprietary products. wolfBoot is well established, has been started in 2018, is very portable. At the beginning, our first port was on a Cortex-M device. So initially we were targeting microcontrollers. Nowadays we can run up to x86 machines as a BIOS replacement, thanks to eFSP support on the Intel CPUs. We support more than 35 platforms, and in addition to that, as we will see, it can run as library anywhere on an existing bootloader that don't have a secure boot solution yet. It has been developed with safety in mind, so everything we will see today implies no dynamic allocations, so no heap usage, no IQ handling unless strictly necessary to the functional steps at the bring up of the system. And the memory usage and the execution flow are at all times predictable at compile time. So that's a strict requirement for safety on projects that are, for instance, life critical. And on top of that, we offer additional security features that are quite unique, like protection against glitch attacks and fault injection, including EMI fault injection. We do offer also some unique features like Delta incremental updates with full emergency fallback, end-to-end encryption, TPM integration on top of other HSM integrations we will see. We do offer certified security, as Shizuka was hinting at, our FIPS 140-3 certificate for our cryptography engine, wolfCrypt, and that's, of course, can be extended to any product that's using the crypto library, including wolfBoot. And wolfBoot itself has been certified for the 0178C up to DAL-A, which is a safety certification issued for airborne software. Backend flexibility again, let's say it runs, let's say, on all kind of embedded platforms up to from the smallest microcontroller you can imagine to the largest PC. Just a few notions about secure boot. What's secure boot? Secure boot in general, as definition from the literature, its main goal is to prevent running unauthorized software on board of the embedded system. So it does that by requiring a cryptographic signature that's attached to all software that's running on board, and that basically can prove that the software is always coming from a trusted source or an authorized source. So a secure bootloader's main goal is to refuse to boot if the software cannot be verified from that's coming from a proven trusted source. How did we do that? When we started developing wolfBoot, there was no standard yet from IETF on how to implement bootloaders. However, there was this group that was studying the problem of implementing secure boot and firmware updates on especially on IoT devices. And of course, the concept can be extended to the entire embedded market. This draft later on became RFC 1919, and that's the document that we have been following since the beginning. And it mandates small parser, it mandates the use of a manifest header. That's very important central thing, as we will see. It implies public key-based authentication to implement the mechanism we just described. The use of a trust anchor, which is basically, in other words, a public key or one or more public keys that need to be protected against, let's say, writing, because they cannot be altered by. They shouldn't be possible to alter the signatures. Sorry, the public keys to guarantee that the authentication is always trusted. And of course, we also have to implement hash-based integrity verification. And one important aspect is that the strategy that's mandated by RFC 1919 foresees that it's the application itself that's in charge of transferring the new image, the update that need to be validated by the bootloader later on. So the bootloader itself doesn't have any communication with the outside world. It expects an application to store the new image somewhere, as we will see. This usually a partition in a non-volatile storage. And the bootloader will take care of authenticating it and installing it or staging it accordingly. How does it work from the key point of view? There's a key pair that's generated once. As we will see, we have tools specific for this operation. The private keys are always stored on a server or on a development machine, and it's never shared or is never transferred to the target embedded system. The public key, on the other hand, is stored in the target, and it's accessible by the bootloader in read-only mode usually. The security depends only on the unique private keys that are used to sign the update. So as long as these keys are not distributed, there is no need for revocation of these private keys. The sign tool is the other tool that we distribute, is responsible for attaching manifest header to the image, and the manifest header also contains a signature, it contains the SHA of the image itself, and some metadata, and that allows the bootloader to verify the integrity and the authenticity of the image. And of course, as we said, the trust anchor is important, that cannot be modified. So what we do to implement secure boot is basically having a private key to sign as mandated by RFC 1919, a public key to verify on the embedded system, and that guarantees that the firmware we are running there or any updates that we send are signed and verified. We have basically two types of updates possible. We have two types of architecture, in fact. We have microcontroller-based devices, which is a typical use in embedded devices, and usually that implies that both the boot and the update partitions are on the same flash memory device. Although, of course, we can store update and swap partitions on a secondary flash. And when a new image is available, we need to physically swap the image of the two partitions, because since the memory is physically mapped, the bootloader expects, the application expects to run always from the same physical address as an entry point. On CPU-based systems, we have another set of typical use cases. So you have usually separate stages to initialize the systems on some more complex systems. And you have two equivalent partitions, basically, and you don't have to move the content of these partitions manually, because these partitions can be remapped. So the bootloader runs an election at boot, basically based on the highest version available among the partitions that can be validated, whose content can be validated in a sense of the authentication and the verification of integrity. And this also often implies interaction with other boot stages, for instance, to keep the chain of trust. So there are, in fact, two main approaches there. The AB approach, where you are electing the best choice for booting based on the available and trusted images in the two AB partitions, or the boot update approach, where the two partitions content need to be swapped, and that's why we use a small swap partition at the end of the flash, usually, which is just as big as one sector. It can be just as big as one physical sector on the flash, to guarantee that there is a fallback. So if you don't confirm that the update has been successful, even if the update can be verified for an actual signature, then we fall back to the last known working version of the firm. So this is more or less how wolfBoot works in a nutshell. Now we will see what actually means to download, compile, configure and compile, and install it on your device. So first of all, we have to download it, and there are two ways to obtain wolfBoot sources. You can go to our download page and retrieve a tarball that already contains all the dependencies, which are other products that we distribute, as we will see. And the other option is to get a fresh clone from github.com. This is usually a if you run this command, you'll get the master branch, which is our development branch. But we make a new release available on average every 3 months. So basically, you can also decide to go to GitHub and download the latest release from the right-hand panel there on the main page. So once you have downloaded the code and you obtain the code, you need to resolve the dependencies. So there are a few dependencies for wolfBoot, and those are all other products that we distribute. If you decided to download the zip from our download page, those repositories will be already included in the source directory under the lib. But if you have downloaded a Git clone, the first thing to do would be to update the submodules. So with the single line command, you can update all the dependencies at once. And basically what will happen is that you get the latest version of wolfBoot, of wolfSSL, the latest version of wolfTPM, PKCS11, and HSM. And those modules are kept in sync. So for instance, the upcoming release, wolfBoot 2.4.0, which should be out today or tomorrow, will be linked to the latest wolfSSL 5.7.6. And we keep tracking, of course, of the previous versions wolfBoot is tied to. And this is because there might be minor changes or new features that we support in wolfBoot that require the latest version of wolfSSL. But through this Git submodules, we can keep those two in sync. So it is not recommended to run wolfBoot in combination with any of the dependency libraries at a different version of the one that's recommended or distributed with the current version. So the wolfscript is mandatory and it's distributed together with wolfSSL and basically provides the cryptography engine that's used for SHA calculations, for public key verifications, and for encryptions, as we will see. wolfTPM, PKCS11, and HSM are optional and basically add interaction with specific HSMs or unlock advanced features. For instance, when wolfBoot can be used as a supervisor for trust zone, it can use wolfPKCS11 to provide an engine of cryptography for the applications that are running in non-secure mode. So once you have all the source tree in place, this should look like this. These are the most important directories there. The source code of the bootloader itself, this is the platform generic source files and some specific assembly bring-up, as we will see. We have include generic header files. We have HAL, which is the hardware abstraction layer, and this contains all the specific targets, as we will see. We have a very extended docs folder where that contains all the documentation and user manuals. There's the tools folder that contains the all the tools that we will talk about for the key handling, image management, and on top of that, also all the test scripts that are used in continuous integration and by us developers daily. And then we have the lib, which contains the dependencies, so the 4 packages that we've seen before. The config, that's where we probably starting from, contains the configuration files and examples for the platforms that are already supported. And the test app directory that contains some simple bare metal applications for all the targets supported in order to demonstrate and test the proper staging once the porting has been completed. Now that we have all the sources, we can start building wolfBoot. And of course, this requires a little bit of configuration. What should be the starting point? This file docs targets.md. contains already instructions to install wolfBoot on 38 different targets at the moment. On most targets are supported through the GNU GCC toolchain. That's the one that we will see a little bit more in details. But of course, we do have support for third-party IDEs, including generic ones like AAR, but also target-specific, platform-specific ones. And for these, there are pre-made projects in the IDE directory, and usually the targets.md will redirect you to that specific project, example project for those targets. When using GCC, we should select the closest existing configuration to the target that we want to support. If you check config examples directory, you will see a lot of different .config files, even more than one per platform, depending on the hardware configuration that we want to demonstrate. So the first thing we can do is basically copy one of those files to the .config in the root directory of wolfBoot and start modifying that .config to match basically the setup that we want to achieve. If we don't have a physical board at hand to test the bootloader, we do have several options. We can use a simulator. We do have a simulator that basically compiles wolfBoot and the application as a executable for your operating system, and then you can run basically all the updates and authentication, parsers, etc. In a process on your OS. We do have emulators. For instance, we use extensively QEMU for richer targets like x86 64 or ARM Cortex-A. And we do have a second emulator that's Renode.io that we use mostly for microcontrollers, which usually we tailor to an RF52 because there the emulator has a bit wider support for writing to the internal flash, which expands the number of tests that we can run on that platform, basically. So once you copied your config file, the first two options that you will see are ARC, that indicates the architecture, and target, and indicates a specific microcontroller or microprocessor. If you started from a target that's close enough, you shouldn't touch the first one because probably it's already in the same family as the target you want to install it to. In the target specifically use an HAL module, so C file and then linker script that are specific for that target. So if the target device is not yet supported, all you have to do, as we will see, is add the HAL driver and then reuse the assembly and everything that's from the targets in the same architecture family. Once architecture and target are defined, the next important thing to decide is the storage layout. So we need to decide how our non-volatile memory geometry will look like. On microcontrollers, in general, or on those systems where you have execution in place and no memory management unit, we do use that swap partition I was hinting at. So you need to define a few parameters to identify the starting address and the size for these partitions. So wolfBoot partition boot address is the start of the boot partition. Then you have to define the start of the update partition. These two partitions usually have the same size, which is wolfBoot partition size. And then you have to set wolfBoot sector size to a multiple of the physical sector, the smallest physical sector among all the NVMs you're using. And the wolfBoot partition swap address is the start of the swap partition and will be as big as the sector size by definition. So on microprocessors, it's very similar, but of course you don't have a swap partition. And the boot address and update address will refer usually to addresses in non-volatile memory. And despite the two different names, those are equivalent. So they are the A and B partitions. So basically, it's not that the system is always running from boot as it happens with microcontrollers, but as we said, there will be an election there. Partition size has the same meaning, the sector size as well. And this load address is basically the address in RAM where the kernel or the firmware will be loaded before staging, and that's always the same. So this allows basically to remap, to copy to RAM the selected firmware and then perform authentication before staging. Coming back to our microcontroller example, that's probably the easiest to look at. This is what you will find in the example configuration for the Nordic NRF52, which we are taking as an example here. And you see that so this is regarding the crypto block on top for now. The wolfBoot partition size is set to 256K, so 0x40,000, where the sector size is as big as 4K, so 0x1000. And you can see that the flash is divided so that wolfBoot, since the first partition, the boot partition starts at 128 kilobytes, 0x20,000, there is plenty of space for wolfBoot to be deployed there. Of course, wolfBoot doesn't need 128 kilobytes. The reason why we use this as an example is because we want to add features, as many features as possible, and with debugging symbols there to test this configuration in the emulator. In production, you probably want to restyle a little bit and get more space for your boot and update partition here. As for instance, I modified the parameters here just to show that we can have a slightly bigger partition, 416 kilobyte, and with the release wolfBoot, 32 kilobyte is still plenty of space, and the space here is a little bit more optimized for the total flash size of 1 megabyte. So you can see just by changing those parameters in the .config file, this is the layout you will obtain. And of course, this is also important for the application to know how big it must be and what is its actually starting point, as we will see, that needs to be aligned to the beginning of the boot partition in this case, because we're talking microcontrollers. Now back at what we skipped earlier. So the sign and hash parameters, those basically are the parameters that decide which algorithms we will use for authentication and the integrity check. So the sign parameter is used to select the algorithm for the public key verification. And as you can see, we have several options. All the options that are supported basically for public key verification by wolfcrypt, including, if you check the last three, MLDSA, LMS, XMSS, that are the post-quantum algorithms that we can use there, also in hybrid mode, starting from wolfBoot 2.3. And the same way, hash indicates the algorithm used to calculate and verify the digest of the firmware image, so for the integrity checks. And in this case, valid choices are, pardon the type, of course, SHA-256, SHA-384, and SHA-3. So the choice of the algorithms, of course, impacts on a lot of things. The first thing is, of course, bootloader footprint. So you can have very small footprint compiled for size optimizations with ED25519 that can be as small as 9 kilobyte, but will be much slower than, for instance, including an RSA equivalent, which will be a little bit towards 15 or 20 kilobytes in size, but much quicker. So you see a trade-off already between the footprint and the boot up time. Another parameter that's also influenced is the manifest header size. So since, for instance, by default, wolfBoot would use a manifest header size of a manifest header of 256 bytes at the beginning of the firmware image. This is not sufficient, for instance, to contain a signature and the hash of a public key and all the other parameters that need to fit in there when you select, for instance, RSA 4096. For this reason, wolfBoot will automatically swap and select a larger image header size. And of course, the image header size is also under your control, so you can select. You can either rely on the default, which is chosen based on the choice of algorithms, or define your own. And if you define your own, you need to add another parameter here explicitly, that's image header size. And for instance, you can decide to have a 2 kilobyte image header. And this, of course, needs to be also communicated to the sign tool when you produce a signed image, because it needs to know how big is the image header that needs to prepend to the application. So, and we do this through command line parameter, so a environment variable, prepended before running the design tool itself. And as you can see, it's the same as the config file, so you could source the config file before running sign. And on top of this, of course, we have seen that in this case, we have shown is only using the internal flash, but a lot of devices, a lot of embedded systems have also external flash. So you can add this external flash parameter. If you set this to 1, it will indicate that it will the wolfBoot will look for an additional API to access external storage that needs to be defined. SPI Flash is one of these example APIs that we provide as a typical usage where you use a generic SPI Flash. So we have some common SPI Flash code that only requires SPI drivers at lower level that we then implement per family of platforms. Let's say we have one for an RF52, one for STM32, etc. So these custom ports can rely on implementing custom external flash functions, and that's what the SPI driver does, but you can do the same in any other way. For instance, we do have another demo that uses a UART to a neighboring system to simulate an external flash. And of course, you can move, update, and swap partition to this external device. When using external storage, you can also activate encryption by adding encrypt equal 1. And then we support 3 algorithms, SHA-20, AES-128, and AES-256. And this is documented also in our docs folder. And we do have examples running both on the simulator and on real targets. You can check how these work. We do have test scripts that also demonstrate how the encryption from the sign tool to the bootloader works. So once we have configured everything, it's time to build. And if we are building with GNU Make, it's just about running Make. Depending on the target, it might have a different default target binary. Usually it's something called factory.bin, which is a single binary file that includes both the bootloader, so wolfBoot bin, and the image, which has been already signed and prepended with the manifest header. And these two are aligned with the selected partitioning, basically. The make file does all this automatically. And behind the scenes, what it does is actually building the key tools, keygen and sign, that we'll see in the next slides. Another additional tool that's been assembly, just to compose the factory bin by adding padding in between the bootloader the end of the bootloader text and the end of the bootloader partition in order to align the first version of the application, and basically automatically also creates the key pair that we will see. So it generates the wolfBoot sign-in private key dot there, and generates what we call a key store. So a key store has multiple different formats, as we will see. So it creates different files that basically have the same meaning. So what you would do is on an embedded target, usually you can place wolfboot.bin and image v1 sign.bin in their respective partitions, or use factory bin that does exactly that, basically by aligning those two. Or wolfboot bin could live in its own ROM or its own flash memory and then have the application somewhere else. So in that case, most likely with the configuration with your target, it will only create a wolfboot bin and the image v1 sign.bin, and then if they need to be uploaded to different locations, that will be explained in targets.md. This was if you were building with the GNU Make. In case you're not, basically a good starting point is running Make, just generating the include target.h, which is a dynamically generated include header that basically contains all the flash geometry that's been taken from the .config. So you have to include that file then in your IDE project, and the project at the same time needs to define some compile time variables, for instance, sign and hash and variables like this that are important for the bootloader to decide which parts, which algorithms to compile in. But we have many projects, as I mentioned, in the IDE directory for AAR, Code Composer Studio, Renesas, IDE, MPLAB X for microchip targets, Xilinx for AMD targets, and Oryx for Infineon Tricore, and many others. So you will see options, you will see different examples of integrating with IDEs easily just by defining some compile time variables and including this target.h that needs to be generated or copied from a make file installation, basically. We have mentioned the key tools more than once now, so it's time to introduce them a little bit more closer. That's a portable set of key tools distributed with wolfBoot. It can be compiled from sources. That's done automatically when you run Make the first time. And we also distribute pre-built exit binaries for Windows that are taken directly from the CI that compiles those from sources nightly. And the most important tools are keygen and sign. And keygen, as we said, generates a key pair, and sign adds a manifest header to the firmware that we need to authenticate. And that's this metadata, including the signature and the hash digest. How do they work? When you want to regenerate your own key pair manually, you can at any time call make keys clean, which removes the default key pair that we created earlier when we run make. And then you can run the tool manually and generate key pairs to add to the key store with the G option, or add existing public keys to the key store for keys that are managed by third party. So if you want to sign your digest using a separate tool, the key gen doesn't need to actually generate the key, but it can include a key that's been generated by someone else. So in this example, for instance, in this terminal line, in the command line, we see how this is used to generate two keys, both boot.key and app.key, and also import a third-party public key from third-party.pub. So the result here is a key store with 3 public keys, and the key stores, so 2 of those are generated physically, created on your disk as boot.key and app.key, and all 3 of them are put in the trust anchor for wolfBoot to use it. The sign tool adds a manifest header, so it calculates the digest of the image, the digest of the public key. It adds the timestamp, the versioning, the signature, the hash of the image, and a number of other things. You can also add custom fields with the command line of from the command line of the sign tool itself. You can add a partition ID. Partition ID 0 is reserved for wolfBoot itself for triggering self-update packages. It does support, as we said, end-to-end encryption if you add the encrypt command line option. And you can also split the procedure. For instance, for that key we're not in control of, if we have a third party that's supposed to sign the digest, we can split the operation in 3 steps. The first step is sign, producing the digest. The second step is your external tool signing that digest, and the third step is the sign incorporating that signature without ever seeing the private key. And this allows, of course, more complex interaction with HSM or HSM as a service that might be needed. So we talked a few times about a key store. We need to specify what actually this is. The key store is just a trust anchor, and it must be embedded in the target. And this can be done in different ways. So you can embed it in the code or store the binary structure somewhere else safe. Usually it can be in a vault, for instance. When you embed it in the code, basically the keygen itself will generate this C file that's linked together with the bootloader. As we see here, we do have both the public key that we imported and the ones that we generated. That's just a snippet of the file. Of course, you would see there is a field pub key as well there. And a few metadata on top that tells about the ID of the key, the permission mask for which partition can be used, the size itself, etc. And the key store is stored on an arbitrary location, so it depends on your project requirements, basically. So it can be embedded in the code, or it can be, as we said, in a separate structure. And in this case, for instance, you will have to provide these 5 functions here on the right-hand side to the bootloader. In this example, we see those that are automatically generated in keystore.c. But if you're using an external source for it, you will have to provide the implementation, for instance, to retrieve the public key from an external device that's not memory mapped. So now we have compiled wolfBoot, we have created the key store, we have deployed the key store. So just this is basically a recap of what we have done. We've done the key gen, we generate the key pair. The private key stays on the server, and it's used to sign the firmware. It also includes the version number, so the version is also part of the sign part, so it can't be altered by an attacker. So that provides protection against rollbacks. And then finally, you obtain the sign firmware that contains a manifest header, and wolfBoot can verify that. How does it work from the deploy point of view? You get this blank device. You put wolfBoot in its own partition at the beginning of the flash usually, and then you put the factory firmware. It can be the version 1, for instance, of your signed firmware. And at this point, you don't need to interact with the device through the JTAG anymore. So you can, for instance, disable debugging, and that's why you're running in production. So no one can touch your bootloader anymore, and the firmware can be updated only by wolfBoot. So on normal operations, you just power on. wolfBoot will verify the firmware image, both in integrity and authenticity, and if everything goes fine, then it will boot into that. While the system is running, it can receive a signed update over the air, for instance, and then store it in the update partition, and then reboot. When you reboot, wolfBoot will verify that there is an update, checks that the new image is newer than the existing one, and verifies the integrity, and then verifies the authenticity. And if everything is correct and the version is bigger than the current firmware running, then we will swap the image. And at this point, our update lives in the boot partition, while the previous firmware is left there as a backup. So that's version 1 in yellow there. And we have version 2 ready to be staged. At this point, the version 2 becomes the current firmware. And from this moment on, if you confirm, the update partition becomes available again to receive the next update. Just spending a couple of minutes on how to port wolfBoot on targets that are not yet supported, what this implies. So as we said, most of wolfBoot code is shared across all the platforms, all the architectures, from smaller microcontrollers to big cloud servers. And then all we need to do is modify 3 simple things. The boot underscore architecture.c is the assembly code for a specific architecture. So we do have one for ARM, one for X5, one for x86-64, and so on and so forth. So this is usually the biggest, the largest amount of work when supporting a new target is if the architecture is not already supported, because of course there is some assembly code required for the architecture, both for the bring up usually and for the staging of the next stage. But since we do support almost all the architectures out there, you should never worry about this. Then you have the update underscore strategy.c, which is the main bootloader flow. And of course, this is a bit depending on the type of the system that you're dealing with. So as we've seen, there's one for swapping the image in place, which is used by all microcontrollers. That's called the update underscore flash.c. Then we have one that is called update ram.c that does the election and the preload, as we said. So we have different flavors. There's one for disks when dealing with partition in a partition table on an actual SATA disk, etc. And usually also you can reuse one of those or slightly modified one of those for your specific use case. That's basically the bird's eye view of the function wolfBoot start that performs the steps to verify and then stage in the correct order and perform the update. And then finally, the hardware abstraction layer, target.c and target.ld, that are target-specific drivers and linker script for mostly for accessing non-volatile and memory and the CPU clock settings for the bring up and for the stage. And the smallest implementation for a HAL driver fits in a slide. In fact, also with a pretty big font, as you will see. This, of course, does nothing, but basically allows you to compile wolfBoot successfully. The HAL init is usually it's called before the wolfBoot start function, and it's meant to set CPU clock settings for the bring up. And the prepare boot is the equivalent before staging. So for deinitializing any peripherals you might have used, so that the application finds the system in the same state as a power on. And then you have the HAL flash write and erase, that are the 2 functions used to access the non-volatile memory, and the optional lock and unlock for those devices that require it. So this is the minimal implementation that you have to provide, and there's of course plenty of different examples for that. But there are cases where, of course, the porting becomes a little bit more expensive. And in some cases, our customers will also ask us, well, we do already have an existing bootloader with already supporting our complex staging and all the bring up and all the drivers provided by the manufacturers, but there is no secure boot in it. And that's where we suggest to use wolfBoot as a library that integrates with your existing bootloader, just adds a few APIs to verify the integrity and the authenticity of the image. And the big advantage there is that you can reuse all our manifest header tools and all our advanced secure boot features and the keygen and sign, etc. And there's documentation on how to integrate this in your existing bootloader. So just a summary, what we have seen today, we know that wolfBoot is modular, very portable anywhere. So you got familiar with the flow, the execution. You can get familiar with that using simulators and emulators target. You can check if your target is directly supported. You can use an existing config, or if your architecture is supported, you start from a closed config and you add your new target just by defining those 4 functions. Or if you have already an existing bootloader and you want to add secure boot features and use all the tools that we already have, you can use wolfBoot as a library. And of course, there is a lot of documentation in docs. And of course, I renew the invite to start from targets.md that explains a little bit more in details what we have seen today for specific platforms. So this concludes my presentation. I think we have a few minutes also for questions. So yes.
Yeah, thank you so much. So there is a question. It is possible to put keys of different types in the same key store.
Keys of different, okay, yes. Yes, basically, as we have seen that the key store supports multiple keys. And in this example I was showing, they are all of the same type. Because we specified the ECC 256 at the beginning. But of course, you can repeat that key algorithm selection before any -G or -I. So you can import keys of different types in the same key store. And this is actually done for hybrid secure boot pairing a classic algorithm like ECC with a post-quantum algorithm like MLDSA. So you get a redundant signature verification using 2 public keys, one pre-quantum, one post-quantum, relying at the same time on the reliability of the ECC, which has no known bugs at the moment, and the post-quantum resistance features of the MLDSA, which is, on the other hand, a new algorithm for definition and implementation. So it doesn't have yet the same level of trust. So that's what in general is recommended when migrating to hybrid. So yes, the key store can store multiple keys at the same time of different types.
Perfect, thank you. There's another question. Can wolfBoot verify the signature of more than one partition?
Yes, yeah. So in fact, I went very quickly on this one. We do have the possibility to have a partition ID. We support up to 15 different IDs. 0 is reserved for the bootloader itself. An ID 1, by convention, is usually the first partition. That's where we are going to stage the application of the operating system. But IDs 2 to 15 are free to use for any purpose and can contain more software or data partitions. So in some cases, even trust anchors. So you can update your keys, basically. So yeah. And the other interesting thing about this is that the key store has a partition ID mask, which basically every bit corresponds to the permission of using that key for that specific partition. So bit 1 will be for partition 0, bit 2 for partition 1, bit 4 for partition 3, and so on and so forth. And partition 2, sorry, so on and so forth. So basically, this way you can have also hierarchical keys, and one public key can only be used, for instance, to update the application, but you need a different type of key to send authentic bootloader or data partitions or other things.
Perfect, thank you so much. There's another question. Can I run wolfBoot as a library from the application to verify updates?
Yeah, that's right. So running wolfBoot as a library is not just for an existing bootloader, as I underlined here in the slides, but you could also link wolfBoot as a library in your application. For instance, some of our customers do that when they receive a new update before rebooting, just to check if the signature checks out, so that they don't do before rebooting, they can decide to discard the received update if the signature doesn't check out, or if only if the integrity, for instance, doesn't check out. So you can call these functions, it's just one C file to add to your application, basically, as described in docslib.md. You will see, so it's not just limited to a bootloader. Of course, it can be linked with an application as well.
Thank you. Thank you, Daniela, for hosting an informative webinar, and thank you everyone for joining the webinar today. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL update by following us on X, connecting with us on LinkedIn, and subscribe to our YouTube channel. If you have any questions, please reach out to us at facts@wolfSSL.com. And thank you again, and we look forward to seeing you on new and updated Getting Started with the Wolf MQTT tomorrow. Thank you so much. Bye.
Thank you. Bye.